Good morning to everyone. This is Rajashekar Reddy, Assistant Professor of Mathematics, Government First Grade College, Pavagada. Now in third semester BCA, we have computational numerical techniques. In the session 38, we discussed about the bisection method. Here also we can find the roots of given equation using bisection method. For example, if you want the real root of an equation x cube minus 2x minus 5 is equals to 0 and the root lying between 2 and 2.5, in the bisection method, how we are going to find the iterative root with desired accuracy. First, the given equation, we take that f of x, a polynomial in x, that is x cube minus 2x minus 5 is equals to 0, and initial value we take that x naught is 2, 2.5 we can take it as x1. First we measure f of x naught, functional value at x naught, that is f of 2. F of 2 value we got minus 1, which is less than 0. Like that we measure f of x1, that is f of 2.5, 4.375 we get, which is greater than 0. Multiplying these two, f of x naught into f of x1, one is negative quantity, other one is positive quantity. If you multiply these two, definitely we get a negative quantity. Whenever you get product of the functional values is a negative quantity, what we can say, the root lies in between the numbers what we selected. That means here we can say the root lies in between 2 and 2.5. So in iterative method, we measure x2 root, approximate root. x2 is nothing but x naught plus x1 by 2. 2 plus 2.5 by 2 is nothing but 2.25. Now we measure f of x2. F of 2.25 is 1.89, which is greater than 0. So whenever here you get greater than 0, in the previous calculations we take negative quantity. For f of 2 we got negative quantity. That's why we say the root lies in between 2 and 2.25. Now we measure in iterative method next root. Next approximate root x3 is x naught plus x1 by 2. That means 2 plus 2.25 by 2. That is 2.125. F of x3 we measure 2.125, that is 0.3457, which is greater than 0. That means here we got greater than 0. In the previous calculations we take less than 0 quantity. For f of 2 we get less than 0, but f of 2.125 greater than 0. That means we say the root lies in between 2 and 2.125. Now we measure in iterative method next root, that is 2 plus 2.125 divided by 2, that is 2.0625. So for this root we measure the functional value, that is f of 2.0625, that is equals to minus 0.3514, which is less than 0. Here we got the functional value is less than 0. That's why in the previous calculations we take the positive quantity, that is f of 2.125. F of 2.125 we got greater than 0, and f of 2.0625 is less than 0. Product becomes less than 0. That's why we say the root lie between 2.125 and 2.0625. So again, the suitable approximation we calculate by taking the average of these two. That means 2.125 plus 2.0625 divided by 2, that is equals to 2.0937. At this value we take functional value f of 2.0937, that is equals to minus 0.0089, which is less than 0. Here the functional value we got less than 0. That's why in the previous calculations we choose positive quantity. For f of 2.125 we got greater than 0. That means we can say the root lies between 2.125 and 2.0937. Root lies between 2.125 and 2.0937. If you want again better approximation, again we take the average of these two numbers, that is 2.125 plus 2.0937 divided by 2. It is 2.1093. At this value again we measure the functional value f of 2.1093, that is 0.16, which is greater than 0. So here we got positive quantity. That's why in the previous calculations we choose negative quantity. Already we know f of 2.0937. For that we got negative quantity. But 2.1093 is a positive quantity. So we can say the root lies between 2.0937 and 2.1093. If you want again the better approximation, suitable approximation, again we measure the average of these two numbers, which is 2.1015. F of 2.1015 is nothing but 0.077, which is greater than 0. So here we got functional value is positive. That's why in the previous calculations we take negative quantity. For f of 2.0937 we got negative quantity. Hence we can say the root lies between 2.0937 and 2.1015. So the same process repeats. We get the approximate value closer to real root, that is 2.0956.